Titrations are a laboratory method where one component of the reaction is very precisely added to the other component in order for the reaction to take place. You can either perform titrations to reach a stoichiometric endpoint, that is where all of the material in the flask equals the material that is added from the burette, where the reaction is perfectly balanced. Many times these can occur in analytical type settings where you want to measure a very precise concentration. By adding a very precise amount of a known solution and knowing the stoichiometric ratio of the reaction, you can determine the number of moles in an unknown solution. This can be done in acid-base chemistry, in complexation, redox chemistry. There are a number of different ways to perform a titration and reach a desired outcome. Many times in this type of titration, an indicator is used that will change color, indicating that the reaction is complete. When you have this type of titration, you would want to get the solution where a single drop of the titrant in the burette will cause a full change in color. Another type of titration, or another method of using a titration, is preparing a titration curve. And a titration curve is measuring a change in a property as you're adding the given solution. This property that you're measuring could be a number of different things based on the chemistry itself. You could be measuring the change in absorbance as you're adding a solution. You could be measuring the change in conductivity as you're adding the solution. Or you could be measuring the change in acidity, or the pH, as you're adding the solution. By doing so, the pH is changing every single time you make an addition of one solution to another. And by plotting this in a titration curve, you can see different regions and where that change is most apparent and where it's weaker. Looking at that titration curve, you can get a lot of information based on that. You can look at the acid constant, or the Ka. You can look at the equivalence point to determine at what point along that graph is the moles of titrant equal to the moles that was in the container. In this experiment, you're going to be looking at a few of these different titrations. You're going to be looking at the titration of a weak acid and a strong base, sodium hydroxide, in order to determine the concentration of that weak acid. The sodium hydroxide is a very precisely known concentration, and you'll very accurately measure the volume. In this way, you can determine the moles of sodium hydroxide that you add, use the stoichiometry to figure out the moles of acid, and based on the volume, you can determine the concentration. You're also going to be looking at the titration of sodium hydroxide with phosphoric acid. Phosphoric acid is a triprotic acid, but you can look at the first two equivalence points. As you do that particular titration, there will be no indicator, and you'll be preparing a titration curve to determine what are the equivalence points and what types of indicators could be used to perform that titration to obtain a specific point. This experiment focuses on acid-base titrations, the combination of an acid and base in a titration format, which is that very meticulous and very precise mixture of the two components. As with all acid-base measurements, this revolves around the pH scale. And the pH reading is a measurement of the acidity of the particular solution. The pH is equal to the negative log of the concentration of H+. So that means the lower the pH reading, the higher the concentration of H+. And the higher the pH reading, the lower concentration of H+. This is a logarithmic scale. It's also log base 10. So to convert from pH back into the concentration of H+, it would be 10 raised to the power of negative pH. When you go through and perform titrations, typically this is done through the use of a burette, where you're combining the two different materials, the titrant in the burette and the analyte in the flask. In each case, you could solve for the number of moles of one of them. If you know the volume of what is in the flask and the concentration, you know how many moles of what is in the flask. If you know the concentration of what's in the burette and how much solution was drained out of the burette to perform the titration, you can solve for the number of moles that was delivered. While most times titrations are performed with the unknown concentration in the flask, it can be the other way around. Either way, you're looking to see what do you have both components of, the volume and the concentration. You'll always have the volume reading from what's in the burette. So that's the final reading minus the initial reading. You'll always have that volume. And a volume in liters times the molarity will equal to the number of moles. Using the stoichiometric ratio of the balanced chemical equation, you can then solve for the number of moles of the other component. These types of titrations are typically done using indicators, where the chemistry is known well enough that a specific indicator can be used where the exact point or the relative point where there is a stoichiometric equal amount is at the desired indicator. And we'll talk about indicators in a little bit. But when you're performing titrations, in theory, what you want is where a single drop from the burette will permanently change the color of the solution in the flask. This particular indicator in this example is phenolphthalein, where under acidic conditions it is completely colorless, and under basic conditions is a bright magenta. So what you're aiming for is that slight pink color where one exact drop of material caused a color change and the start of that color change. This one is pretty well defined where you can see exactly when it's over titrated. If you get to that bright fuchsia color, it's over titrated. You added too much of the base and now it's very, very dark. You want to get to that very faint color indicating that it is just at the end point and not anywhere over. Titrations use burettes, and burettes have the The readings on a burette are based on what is delivered or what leaves the burette. The top marking when a burette is filled is marked as 0.00 milliliters. Nothing has been removed from the burette. Nothing was delivered to that flask below it. And as you're draining solution and it's reacting with the solution in the flask, the volume in the burette is lowering, but the number is increasing. The numbers are read down. So once you reach this exact endpoint, you can then stop the burette and look at what is that final reading. The volume that was delivered is the final reading of the burette minus that initial reading. While it is very easy when the initial reading is exactly 0, it doesn't always have to start at 0. So that way, when you perform the calculation of final minus initial, you'll always end up with the volume of the titrant solution from the burette. And you can use that volume to determine moles of one component and then moles of the other component using the stoichiometric ratio. In an acid-base titration, when you're using an indicator, that tells you when the pH of the stoichiometric endpoint is reached. But what if you don't know what that pH is? You wouldn't be able to use the appropriate indicator. This is where a titration curve can be very, very useful. A titration curve is where you're continuously adding the amount of material to the reaction and measuring the pH. You can build a titration curve with other measurements, but in an acid-base titration, the y-axis, or that change in property, is the pH of the solution. And as you're adding more and more base to the acid, the pH will be increasing, because increasing pH means a higher level of alkalinity or a lower acidity level. And it will increase by a certain amount and then jump and then continue on, almost leveling off. It's this jump, the inflection point, right in the middle of this jump, that is the equivalence point. That is the pH reading where the moles of sodium hydroxide is equal to the moles of acid that was in the flask. So in this case, here is the exact equivalence point, about 8.25, at exactly 0.1 moles. So in this particular titration of 0.1 molar acetic acid with sodium hydroxide, the equivalence point was about 8.25 based on this graph. So when you would be choosing an indicator where you want to know at what point are the moles of acetic acid equal to the moles of sodium hydroxide, an indicator would be chosen that changes color at approximately this pH. These titration curves are performed without the use of an indicator because you're using the curve itself to figure out what type of indicator would this style or this type of titration be useful with. Now, I mentioned that inflection point on the titration curve, that equivalence point. The equivalence point is the exact stoichiometric point where the moles of the two components are equal to each other. So the moles of the titrant is equal
to the moles of the analyte or the solution in the flask. The equivalence point, so when things are, when it's asked what the equivalence point is, this is the pH reading. That would be constant. No matter how much material you start with, the equivalence point of that pH will always be the same. If you start with more acid, it will take more moles of base to reach that point. So the Y value, that pH point, would be the constant equivalence point. And when you have the molarity of the titrant and the volume of that titrant from the burette, you can determine the moles of the titrant. And when you have that, you can multiply it by the reaction ratio of the particular reaction, and that will give you how many moles of material is in your flask. So going through in a sample calculation, if there is exactly 35.00 milliliters of a nitric acid solution, and that is titrated with 0.250 molar sodium hydroxide until the endpoint is reached. So until it's titrated until that equivalence point is reached. The volume dispensed is 27.75 milliliters. What is that concentration of nitric acid? So first, look to see what you have. There are two components, each with a volume and a concentration. You have nitric acid and you have the volume of nitric acid. And you're mixing that with sodium hydroxide. You have both the concentration of sodium hydroxide and the volume of sodium hydroxide. Because of that, you can use the molarity and the volume to solve for how many moles of sodium hydroxide was used. Then you do need to know the balanced chemical equation. Looking at the balanced chemical equation, 1 mole of nitric acid will react with 1 mole of sodium hydroxide to produce 1 mole of sodium nitrate and 1 mole of water. The reaction ratio between these two components is 1:1. So if you multiply your moles by the reaction ratio, you will end up with the moles of what you actually want. So this is a 1:1 ratio. So the moles of sodium hydroxide is equal to the moles of nitric acid. Now you have the moles of nitric acid and you still have that volume. It's the volume of nitric acid that you started with. The number of moles did not change, but as you were adding the sodium hydroxide, the volume changed. These are typically asking, what is that initial volume? Before you started adding the sodium hydroxide, what was that concentration of nitric acid? So if you have moles of nitric acid and you have the volume of nitric acid, you can then divide the two and determine the concentration of a nitric acid solution. Titrations are used in this general setup for a lot of different unknown calculations. Again, you'd have the volume and concentration of two different components, what's in the flask and what's in the burette. You would need to identify which one of these components gives you both of these measurements, the concentration and the volume. From that, you can determine moles of that component, use the balanced chemical equation and multiply by the stoichiometric ratio to equal the moles of the other component. And now that you have moles of the other component and either volume or molarity, you can solve for that final missing piece of the puzzle. Because this is a strong acid, the number of moles of nitric acid equals the number of moles of H plus ion when it dissolves. Therefore, the concentration of H plus is also the same as the nitric acid, 0.500 molar. By taking the negative log of 0.5, we could determine the pH at the very beginning, the very starting pH is 0.301. The next step along a titration curve is are the values before the equivalence point. So each time you need to determine how many moles of base are added. So in a spot before the equivalence point, let's say at 10 milliliters of sodium hydroxide is added, you would solve for how many moles of sodium hydroxide were added, the concentration of the sodium hydroxide times whatever volume was added. All of this sodium hydroxide would be reacting with the nitric acid in a 1-to-1 ratio, still looking at that stoichiometric ratio. So knowing that there was 0.0125 moles of nitric acid to start with, and 0.005 moles have reacted, that means that there is now 0.0075 moles of nitric acid remaining in that solution. There's also a new volume though. Now, you used to have 25 milliliters, but an additional 10 milliliters of volume of liquid was added. So the new volume is now 35 milliliters. So there's a new number of moles and a new volume. You can take the moles, divide it by the volume to obtain the new concentration of nitric acid. And in this case, it would be 0.2143 molar. By taking the negative log of this, you can solve for the new pH of the measurement, 0.669, still a very acidic condition. Next is what would happen at exactly the equivalence point. So this would be where the moles of acid is equal to the moles of base. If you have 0.0125 moles of nitric acid, this means the equivalence point will be when exactly 0.0125 moles of sodium hydroxide is added. So the moles of base is equal to the moles of acid. This is a strong acid and strong base. The only equilibrium that's taking place here is the equilibrium of water itself. H plus OH minus yields water. So the pH of that perfectly neutral solution then would be a pH of 7. In all strong acids, strong base titrations, the equivalence point will always be a pH of 7 because this is the only equilibrium that's happening. After the equivalence point, in, let's say this case, 40 milliliters of base is added. So first, as always, solve for how many moles of that sodium hydroxide was added. We still have the same concentration that we're starting with, 0.500, and multiplying that by the volume of 40 milliliters. So a total of 0.02 moles of sodium hydroxide was added. There was 0.0125 moles of the nitric acid, and that had to react with the stoichiometric amount of the sodium hydroxide. So by subtracting the two, this amount has reacted and you are left with 0.0075 moles of sodium hydroxide in that solution and a new volume of 65 milliliters. The 25 initially plus the 40 that was added, so the new volume. So we could solve for the concentration of this sodium hydroxide. We have the moles and we have the volume. The concentration of the sodium hydroxide is 0.1154 molar sodium hydroxide. This is a typo. When we look at the concentration of the sodium hydroxide, we can obtain the pOH. That's the negative log of the concentration of hydroxide. And when we do that, we find the pOH is 0.938. Since the pH plus the pOH is always equal to 14, you could solve for the pH itself, 14 minus 0.938. And that gives a pH value of 13.06. Throughout this whole curve, throughout this whole titration, you could incrementally increase this from 0 all the way to 50 milliliters and solve for the pH at every individual point and prepare that graph. And that should mimic the same type of a titration graph that you would measure in a laboratory setting. The other type of a titration would be between a weak acid and a strong base, where the strong acid, strong base combination only has the equilibrium of water to look at. A weak acid has its own equilibrium. The acid itself does not ionize 100%. So when it's in solution, there is an equilibrium between the acid and its conjugate base with H+ on the other side. And that's where the Ka, or the acid dissociation constant, would come into play and play a role in determining the pH throughout these titration curves. The sequence, though, of obtaining the different values is the same. You're looking at what are the initial conditions before any base is added. How would you find the pH before the equivalence point, at the equivalence point, and then after the equivalence point? The initial conditions are just looking at what is the pH of a weak acid solution. And you've already worked on these sorts of problems. If you have the Ka of that acid solution, you can solve for a simpler ice table where you have the initial concentration of acetic acid as given in the sample, given in the question, and you would have an initial concentration of acetate and H+ as 0. Based on Le Chatelier's principle, this side of the reaction would increase while the acetic acid decreases, all by the same amounts. So knowing what the Ka of the weak acid is, you could solve for the X value. You'd have the Ka is equal to the acetate ion times the H+, divided by the concentration of whole acetic acid. This is all at the equilibrium. So since the acetate and H+ are will be the same concentration, you're multiplying it by itself, divide it by that 0.5 molar acetic acid minus X. So if you were to work this out, you would find that the X value is 0.00295. And that is the concentration of H+, which you could solve which you could obtain the pH from. So the pH of this starting acetic acid solution is 2.53. The next sequence, or the next area of the titration curve, would be the area before the equivalence point. And in still using the same volume, 10 milliliters of a 0.5 molar sodium hydroxide solution, you could look at this in terms of moles. Every time the sodium hydroxide reacts with acetic acid, it will produce the water and that acetate ion, that conjugate base. So you have here the moles of acetic acid is 0.0125, same as in the previous example. The 0.5 molar acetic acid times 25 milliliters. And when you add 10 milliliters of sodium hydroxide, it's 0.005, the 0.5 molar times 10 milliliters. Since that is going to react with the acetic acid, you're subtracting the two to find out how many moles of acetic acid are left after the reaction. However much did happen to react, that's how much of the conjugate base was produced. And now you have this combination of a weak acid and its conjugate base. This system before the equivalence point is a buffered system. And you can treat this just as a buffer. So now you have 0.0075 moles of acetic acid and 0.005 moles of the acetate ion. The OH of the sodium hydroxide react it with the H plus to generate water. So the initial concentration is still 0, but there's a new volume, 35 milliliters. You add it 10 more milliliters of volume. So you could solve for, first, what are those new starting conditions, those new initial concentrations based on these new number of moles of both acetic acid and acetate, and this new volume. You're still going to be doing following that equilibrium and following Le Chatelet's principle, you're going to be increasing this side and decreasing the amount of acetic acid. So you'd have the concentration of acetate plus some amount times some amount of the H plus. This is what's going to be gaining because you're starting at 0. So that's how you know it's going to be added. The change is going to be adding to the side of acetate and H plus. And since you're starting with 0.214 molar acetic acid, that's going to be subtracted. So now you have this worked out where the Ka is equal to 0.143 plus X times X over 0.214 minus X. And when you work through and solve this out, you'd find that X is equal to 0.0000262. And that X is the concentration of H plus, and you can solve for the pH of 4.58. There is a more simplified way to do this, however, and that is to use the Henderson-Hasselbalch equation. And this equation looks at the concentration of base, the concentration of acid, and it involves the Ka and the pH. You're looking at all of this and using these ratios to solve for a particular pH. So the Henderson-Hasselbalch equation is that the pH is equal to the pKa, that's the negative log of the Ka, plus the log of the concentration of base divided by the concentration of acid. This is typically only works when X is considered small, and for most situations. So in this example, we already knew the Ka. The Ka for the acetic acid was 1.75 times 10 to the negative fifth. So the pKa of that is the negative log of 1.75 times 10 to the negative fifth. The pKa is 4.76. Now we worked through this out. We knew that we had 0.0125 moles of acetic acid, and some of it reacted, and we were left with 0.0075 moles of acetic acid, and 0.005 moles of acetate was generated over a new volume of 35 milliliters. So we already looked at that as the initial concentrations previously. We saw these initial concentrations of acetic acid and the acetate. And that's what you're going to be plugging into the Henderson-Hasselbalch equation. What are those initial concentrations once they've been diluted because of the new volume? So if we take the log of the concentration of base, 0.143, that's the conjugate base, the acetate, divide it by the concentration of acetic acid, 0.214, we end up with that same pH value, 4.58. This Henderson-Hasselbalch equation can also be very useful in determining what is the Ka of an equation if you are measuring the pH in the lab. So in a laboratory setting, you can measure the pH of the lab, or the pH of the solution in lab, and determine these moles based on what you've added together. You can determine how many moles of acid are in the flask, how many moles of base was added, so therefore how much acid is left and how much conjugate base was generated, and divide that by the appropriate volumes. And if you have the pH and this ratio, now you could solve for the pKa, which you could use to find the Ka. So using this Henderson-Hasselbalch equation, you could solve for what is the K, what is the acid dissociation constant of a weak acid. And you can look at that based on any of these titration curves. Once you reach the equivalence point of a weak acid and strong base titration, the number or the moles of acid is equal to the moles of base. That's what the equivalence point is, where the moles of acid are equal to the moles of base. So now all of the acetic acid is converted into acetate ion and water. So now you're looking at the reverse reaction, or the reverse equilibrium. You have a Kb, the base as a reactant going into the acid as a product. So the Ka times the Kb will equal Kw, that the dissociation constant of water. And so if you know what the Ka is, you can solve for the Kb, the base dissociation constant. The Kw of water, the equilibrium constant of water, is an absolute constant, 1 times 10 to the negative 14th. So if you know the Ka, the equilibrium of the acid turning into the base, you can solve for the Kb, which is the base turning back into the acid. And using this Kb, you can solve for the new moles of the acetate and acetic acid. The Kb is equal to, again, products over reactants. So the products are now acetic acid and hydroxide, and the reactant is the acetate ion. You have the Kb, and you're going through and solving just as you would under a normal Ka conditions. When solving for x, we have x is equal to 0.00001196. That is the concentration of OH minus. And if you have the concentration of OH minus, you can obtain the POH. And from the POH, you can subtract that from 14 to obtain the pH value. So under these conditions, at the equivalence point, the pH of the solution of acetic acid will be 9.08. The last step is looking at the sequence of what is the pH after the equivalence point. And after the equivalence point in these weak acid strong base titrations, that strong base is very overpowering. It's overpowering anything associated with that weak acid. And it's much, much more straightforward. You already know that there is 0.0125 moles of acid, and you mixed that or added 0.02 moles of base. So by subtracting them, you realize that there is 0.0075 moles of OH minus additional after everything has been reacted. If there's this many moles of the strong base remaining, and now a new total volume of 65 milliliters, this gives a concentration of hydroxide as 0.1154 molar. With the concentration of hydroxide, you can determine the POH, and finally the pH of the solution, which would be 13.06. So in summary, at the start of the titration, if you know the Ka, you can determine the pH through the ice table. And if you know the pH, you could determine the Ka through the equilibrium equation. Before the equivalence point, a strong base will react with the weak acid in a stoichiometric amount and become a buffer. And you can solve for the change in those moles. How many moles of acid reacted, and that's how many moles of conjugate base there now are. With those new starting moles of acid and moles of base and a new concentration or a new volume, you can solve for that initial concentration and work through an ice table. So if you have the Ka, you could solve for the pH using that ice table and these new concentrations. Or if you have the pH, you could do the same thing and solve for the Ka. You can also use the Henderson-Hasselbalch equation as a more simplified way to work through this, looking at where the pH is equal to the pKa plus the log of the concentration of base over the concentration of acid. At the equivalence point, this is where the moles of acid is equal to the moles of base. So now you're going to be looking at what is the equilibrium of all of that base converting back into some of that acid. Again, these are all equilibrium systems. So with the Ka of the weak acid, you could solve for the Kb of its conjugate base, and then determine through another ice table what the equilibrium concentration is of the OH minus, and solve for the POH and finally the pH. And then after the equivalence point, you can treat it just as the excess of the strong base. You have the base that was added reacting with all of the acid, so the remaining base can be used to determine the new concentration of OH minus, and therefore a POH, and finally a pH. So with all of those calculations that could go into a titration curve, it is much more convenient when all of these things might be known already, and an indicator can simply tell you when a reaction has reached the equivalence point. Most times when performing an acid-base titration, these solutions are clear and colorless. There's no indication of when the products or when the reactants turn into the products. They look exactly the same. And that's where an indicator can visually tell you when the pH has reached that equivalence point. An indicator itself, like phenolphthalein here, is a specific chemical where the structure is oriented in such a way that it can produce a color under the right conditions. So many times these are organic molecules, and it will have what's called conjugation when it displays a color. If you look at the chemical structure of this indicator molecule under high concentrations, or a high pH, I'm sorry, there is what's called conjugation, where it's an alternating single double bond sequence throughout the whole structure. At lower pHs, that's where the concentration of H plus is higher, there is a Ka associated with the indicator at some of these points. And when the Ka is reached, or the concentration of H plus is reached where this variant of the molecule is present, that conjugation, that large amount of alternating single and double bonds, is broken. And because it's broken, there is no color. In this particular indicator, it goes from alternates between colorless and light pink or fuchsia in color. However, there are a lot of different indicators, and they come in a wide variety of different colors. Some of them go from colorless to a color, others go from one color to another. And where this change takes place, where this color change takes place, is unique for each different type of reactor. The pH where that transition actually happens is different. And so that way, in a situation where the equivalence point is at exactly 7, one indicator would be best. If the equivalence point is at 9, a pH of 9, a different indicator would be best. And knowing what indicators change color at what pH can greatly help in a lab setting when you're looking at a titration, and it can reduce the number of all of those calculations that might need to be involved if you were needing to calculate an actual pH curve.
Indicators are chemicals that have a color property associated with their chemical structure. Under certain conditions, the structure of the chemical itself is such where there is no color. All of these solutions are slightly acidic at the moment. However, depending on the indicator, by adding additional base, the color can change for these different solutions. Knowing what indicators are present and at what pH they change color can give a good indication of where an endpoint would be. These different indicators all change color at a different pH. They're mixtures of a few different indicators to produce these types of colors. But overall, indicators will change color at a different pH level, so you can use that indicator range to determine when is the most appropriate pH to use a particular indicator. All of these beakers contain the same approximate amount of 0.1 molar acetic acid. The pH of the acetic acid is about 2.3. Using these different indicators, you can see which ones have a color under these specific conditions. Thymol blue, phenolphthalein, universal indicator, bromophenol blue, bromocresol green, and phenol red. They all have their unique color in these particular conditions. However, upon the addition of sodium hydroxide, the color will begin to change. If you noticed, after a few drops, the color starts to change and then instantly goes back. You can begin to see a change now in the bromophenol blue. However, the others still remain relatively close to their original color. The universal indicator is also beginning to change. Now, the bromocresol green is beginning to change its color. The universal indicator is now a yellowish color, and the phenol red has now changed color. The universal indicator and the phenolphthalein both have been able to change color, as well as the thymol blue. All of these indicators had the same starting conditions, but changed their color as the sodium hydroxide was added. The pH of all of them is still approximately the same because approximately the same amount of sodium hydroxide was added. However, each of these indicators will change color at a different pH. Knowing what the equivalence point is dependent on knowing which type of indicator to use, which will change color at approximately the pH of the equivalence point.
So as was seen in the video, there are a lot of different indicators, and that was only a small sampling of the different indicators that are available that change color under different pH environments. So there are a number of different charts where you can see what colors the different indicators are, where they have their transitions, and that way you can tell which indicators would be best to use at which equivalence points. So in the case of phenolphthalein, the color change range is between 8.2 and 10, and it goes from colorless to that bright pink or fuchsia. So right around here, around pH 9 or so, is perfect for phenolphthalein. If you had something where you were looking at a pH of about 4, there are a few you can choose from. Methyl orange is all right. Bromophenol blue works. Congo red is good. So there are a few different things. But as you move farther down here, methyl red, maybe not quite, because by the time you get to pH 4, it hasn't quite changed color yet. Here with thymol blue, once you get to pH 4, it's beyond where that transition happens. So you want to choose a pH or choose an indicator that has its color change right around your equivalence point. So when you're mixing things together, a good rule of thumb to look at is the type or the location on the pH scale of where the products would be. And that can generally tell you what indicators you could choose from. A strong acid and a strong base will always produce a neutral product. So something along the lines of thymol blue would probably be pretty good. A strong acid and a weak base would produce an acidic product. So these indicators right here would be a good choice depending on what the actual equivalence point is for the particular chemistry. And a weak acid and strong base produce a basic product. So these indicators down here would be good for that type of a titration to tell you when the equivalence point has occurred based on this visual observation. And you can look at these equivalence points and choose which indicator would be best for your equivalence points. In the experiment itself in lab, you're going to be performing a couple of different types of acid-base titrations. In the first part, you're going to be titrating potassium hydrogen phthalate, which is a weak acid, but you're going to titrate a known amount, and using the balanced chemical equation and the known stoichiometric point, You're going to titrate this using an indicator to determine the equivalent weight of your particular unknown sample. In the second titration, that's where you're going to be generating a titration curve of phosphoric acid with sodium hydroxide. In the first part, you're going to be looking at titrating potassium hydrogen phthalate, or abbreviated KHP, with sodium hydroxide in order to determine the equivalent weight of an unknown. Now, all of the unknowns that are listed are, or all of the unknowns in lab are this potassium hydrogen phthalate, but in differing amounts. There's a filler in there as well. And you're going to perform the titration to determine its equivalent weight. The equivalent weight itself is kind of an older definition used in acid-base chemistry. The equivalent weight is the mass of an acid that 1 mole of base can react with. As such, the units of equivalent weight would be grams per mole. So there are a couple of ways you can calculate the equivalent weight. One is from the measurement itself. You're going to weigh an amount of an acid sample and then perform a titration. At the stoichiometric point, the indicator will change color, and you can determine how many moles of base were used to react with that mass of the acid. So from the experiment in lab, the equivalent weight is going to be equal to the mass of the acid, which is weighed out just directly on the balance, divided by the moles of base. And this is coming from the concentration of sodium hydroxide and the volume of sodium hydroxide from your burette. You can also determine the equivalent weight just based on the chemical structure itself. So the equivalent weight, again, that's the mass of an acid that 1 mole of base can neutralize. So think of hydrochloric acid. The molecular weight of hydrochloric acid is 36.5 grams per mole. For every 1 hydrochloric acid that can react with 1 mole of sodium hydroxide, there is 1 proton on hydrochloric acid. So for every 36.5 grams, that's 1 mole of hydrochloric acid, it can react with 1 mole of base. So the equivalent weight is 36.5, the mass, divided by 1, the moles. And they're the same. For a diprotic acid, that's something that has 2 protons on it. The equivalent weight is equal to the number of those protons. So in the case of sulfuric acid, 1 mole of sulfuric acid weighs 98 grams. But there are 2 protons associated with it. For every 1 mole of sulfuric acid, 2 H+ will come off and react with the sodium hydroxide. Therefore, 1 mole of sodium hydroxide would be able to react with half of that acid, 49 grams. So the equivalent weight is equal to the molecular weight divided by the number of protons that are on the chemical structure. In the case of the potassium hydrogen phthalate, the chemical that you'll be working with in lab, this structure is a carboxylic acid structure. And this H is what breaks apart and breaks off and reacts with a sodium hydroxide. For every one of these potassium hydrogen phthalates, it can react with one hydroxide. Overall, the net ionic equation is still the H plus that breaks off plus the hydroxide gives water, and you're left with just the phthalate ion.
In the lab experiment, to measure the equivalent weight, you're going to be given an unknown sample and determine its equivalent weight by titration. You're going to be performing 4 titrations of the same material. As the procedure is written, to measure out the mass of sample used in each trial, you can simply weigh the entire container and obtain the starting mass. With the starting mass of the container and the sample known, you can then remove some of the material and add this to your Erlenmeyer flask. The amount of material added should be between approximately 1/2 and 1 gram. You can then weigh the entire container again. The difference between the first and second weighings of the container is the mass of powder that was added to the flask. You can then dissolve this powder in 50 to 100 milliliters of water. If it is beginning to be a little bit too difficult to dissolve, you can place it on a small hot plate, and that should increase the solubility. But once the sample is dissolved in the water, it's ready to begin the titration. To begin the titration, you will fill the burette with the standardized 0.1 molar sodium hydroxide solution. The concentration of this solution is known to 4 significant figures, so please be sure to record the correct concentration given on the sodium hydroxide container. To begin the titration, you will add about 5 to 10 drops of phenolphthalein indicator to the flask. This indicator solution is colorless in acidic solutions and turns a pink color in basic solutions. When the solution color turns pink, the titration is complete. In the lab on the dark benchtops, it may be useful to add a white piece of paper below the flask. In this way, you will very easily notice when the solution turns pink and remains pink. As the sodium hydroxide is being added, you can see this pink color starting to form and then instantly going away. The titration is complete when the pink color remains in the solution. As more and more sodium hydroxide is added, the pink color remains for a longer and longer period of time. The key to a very accurate titration is to have the faintest color possible to ensure that everything is used up, all of the acid is used up and reacted with the base, and you've reached the equivalence point where one additional drop of the sodium hydroxide solution will cause the pH of the flask to increase beyond the indicator's color change point. The pink color should remain for approximately at least 30 seconds to a minute, and at that point, you can consider the titration complete. Again, you want to aim for a very light pink color. This is the point where all of the sodium hydroxide has reacted with the potassium hydrogen phthalate, or with the acid in the flask. And now the additional base is causing the indicator to change to the pink color. If you over titrate, and that is you add more base than this exact equivalence point, the solution color will become very, very dark. This very, very dark color would be an indication of an over titration and will skew your results. If in your 4 trials you have one obviously over titrated sample, you can perform a 5th titration to make sure that your final equivalent weight is accurate.
So in the lab setup, you're going to be obtaining the mass of your unknown sample. First, record down whatever your unknown number is and obtain the mass of sample that you're using in each individual titration. And to do that, you're going to be weighing by difference. You're using a number of flasks to perform the titration, and they may be wet. So those wet containers will cause variation if you were to place those on the balance. So this is why you're weighing by difference and adding it, or adding that solid powder to your flask. What you can do is weigh the entire sample container, remove some of the sample and place it into your flask, weigh the entire sample container again, and the difference of that mass will be the mass of powder that you added to the flask itself. You're going to dissolve your sample in an amount of water, and then add about 5 to 10 drops of the phenolphthalein indicator. You're then going to titrate with a standardized solution of sodium hydroxide. This solution is available in lab, and it has been meticulously standardized. That is, the concentration is very precisely known. The concentration of that sodium hydroxide solution is known to 4 significant figures. So you should be determining the equivalent weight all the way out to 4 significant figures and performing all calculations to that, at least that level of precision. So you'll use the standardized sodium hydroxide to titrate, and then determine how many moles of sodium hydroxide were used by multiplying that specific molarity times the volume from your burette, and determining the equivalent weight of your particular sample. That's the mass of your sample divided by the moles of sodium hydroxide. You're going to do 4 titrations and obtain an average equivalent weight of those 4 values. If one of the titrations does happen to be quite off, you can tell that it was over titrated, then you should be able to do a 5th titration as well, just to make sure that your averages are more accurate. Now, the potassium hydrogen phthalate itself is a monoprotic acid. There was only one H plus for the entire molecule, so it was a 1-to-1 ratio. The molecular weight of this potassium hydrogen phthalate was equal to the equivalent weight. But What would happen if it is a polyprotic acid or diprotic or triprotic? For this one molecule of phthalic acid, there are two hydrogens that can break off. So this 1 mole of acid would react with 2 moles of hydroxide and still produce the phthalate ion and 2 moles of water. The net ionic reaction is still the same because it's 2H plus will react with 2 hydroxides to give 2 waters. So overall, the net ionic reaction is still the same. All of these acid-base reactions have the same net ionic equation. H plus OH minus yields water. So knowing how many protons are available on a particular acid will indicate how many hydroxides can actually react with it. So many times there are monoprotic acids, hydrochloric acid, nitric acid, the acetic acid, and potassium hydrogen phthalate all have 1 proton associated with them. Diprotic acids include sulfuric acid, which is the only strong acid here, but also carbonic acid, this phthalic acid, or oxalic acid. And a triprotic acid would be phosphoric acid. And that's what you're going to be looking at in the second part of the reaction or of the experiment. In the second part of the experiment, you're going to be preparing a titration curve of phosphoric acid and sodium hydroxide. You're going to use the pH meter as you used in the previous experiment and measure the pH over 25 different points. So first, you'll prepare a solution of phosphoric acid and then measure what the pH is and add sodium hydroxide from a burette 1 milliliter at a time and measure 25 points. And in this way, you're going to be obtaining the titration curve of the phosphoric acid. So in here, you have phosphoric acid, which is a triprotic acid. 1 molecule of phosphoric acid will react with 3 sodium hydroxides to produce 3 waters and sodium phosphate. Phosphoric acid itself is a weak acid. And because of that, each one of these individual protons, these individual H plus ions, has its own Ka value. It is these Ka values from polyprotic acids that are weak acids form a stepwise function. Phosphoric acid will first turn into dihydrogen phosphate ion. And this has a particular Ka associated with it, the equilibrium between phosphoric acid and its conjugate base of dihydrogen phosphate. Now, this ion is still very acidic, even though it's a conjugate base relative to the phosphoric acid. It would still have be in an acidic solution. This is a conjugate acid, though, with respect to monohydrogen phosphate. So as the dihydrogen phosphate loses 1 more proton, there is a second Ka. So there is an equilibrium between the dihydrogen phosphate and the monohydrogen phosphate. And because it's a triprotic acid, there's a third Ka between the monohydrogen phosphate and just the phosphate ion. So while this is more acidic and this is more basic, each one of them is a conjugate acid-base pair. Now, in this titration, you're not going to be able to see this third step. This one is very difficult to see, but you will be able to see the first two steps of this titration curve. So in the past, where you've seen a titration curve that only has before the equivalence point and then after the equivalence point, this is a diprotic curve. There are going to be two Ka values from it. Phosphoric acid turning into dihydrogen phosphate, and then dihydrogen phosphate turning into monohydrogen phosphate. When you look at this curve, you can treat it as two separate titration curves. And you can look to see, based on that curve, look at your data, look at your graph, what is the equivalence point of this equilibrium, phosphoric acid going into dihydrogen phosphate, and what is the equivalence point of dihydrogen phosphate going into monohydrogen phosphate. Using your graph, you can determine what the equivalence point is, what the equivalence points are for these two steps. You can determine what sort of indicator would be appropriate to use in each of these individual titrations, or to determine when the equivalence point is reached. And you could also use the Henderson-Hasselbalch equation before this equivalence point and before this equivalence point in between, to determine what these actual Ka values are. Using the Henderson-Hasselbalch equation, your measured pH and the moles of acid, or I'm sorry, the molarity of the acid and molarity of the base.
In the experiment, you're going to be preparing a titration curve of phosphoric acid. You're going to be titrating 0.1 molar phosphoric acid with 0.5 molar sodium hydroxide. You're going to be measuring the pH of the combination of the two with every milliliter of sodium hydroxide that's added. You'll measure out 50 milliliters of your 0.1 molar phosphoric acid solution and add that to your Erlenmeyer flask. You can then measure the pH of this solution, or of this phosphoric acid, with 0 milliliters of the sodium hydroxide added. When you're measuring using the pH meter, you should always make sure that it has been calibrated since you plugged it in. If you're just starting to use the pH meter, you will need to go through the calibration procedure before you begin the measurements. Once the calibration of the pH meter is complete, you can then record the pH of the phosphoric acid. In this case, the pH is 1.30 or 1.29. You can then begin to add the sodium hydroxide from the burette. You're going to add exactly 1 milliliter of the sodium hydroxide. And record the pH again. Once the indicator says ready, you can move on to the next titration, or the next addition. You will add again 1 milliliter of sodium hydroxide, swirl the flask, wait for the measurement to stabilize, and record the pH reading. You're going to add a total of 25 milliliters sodium hydroxide and record the pH at each interval. With the pH recorded, you can then prepare a calibration curve with pH on the y-axis and the moles of sodium hydroxide added on the x-axis. Once you have the titration curve for the phosphoric acid, you can determine the equivalence point, and at any point along the titration curve, you should be able to calculate the equilibrium concentration of everything in the solution. The hydroxide, the phosphoric acid, its conjugate bases, and H+.
So as you saw in the lab itself, you're going to be adding 50 milliliters of a 0.1 molar phosphoric acid solution to a flask and measuring its pH. You'll also be filling a burette with 0.500 molar sodium hydroxide. Be mindful of the concentrations you're using. You're performing two different titrations in the experiment, and there are two different concentrations of sodium hydroxide present in the room. The large container is for part A, and the separate smaller bottles, the individual bottles, are for part B. So you're going to titrate this 50 milliliters of phosphoric acid with a total of 25 milliliters of 0.5 molar sodium hydroxide. Each time you add exactly 1 milliliter from the burette, you'll pause and record the pH again. This way you can prepare a graph of the measured pH value on the y-axis versus the moles of sodium hydroxide that were added. And from that, you can determine the first two equivalence points. You can determine the indicators which would best be used to indicate those two equivalence points, and calculate the two Ka values of phosphoric acid based on your titration. So in the end, you're looking at these two different titrations. You're looking at an acid-base titration purely to determine an unknown. You're looking at a known reaction with a known indicator and using it to determine the endpoint, the equivalence point of that particular reaction, where the moles of base is equal to the moles of acid that you've weighed out. So you'll obtain the mass of your sample, dissolve that in water, and titrate that with sodium hydroxide, a very standardized and precise concentration of sodium hydroxide, and use that to determine the equivalent weight of 4 different titrations and then obtain the average. The second part of the experiment looks at preparing that titration curve. You're looking at the titration of phosphoric acid with sodium hydroxide. There's no indicator for this particular titration, so you're going to be measuring the pH with each 1 milliliter addition up to a total volume of 25 milliliters added. From your titration curve, you'll be able to visually see on your graph where the equivalence points are. What is the pH of those points? The equivalence point is the pH value, so the y-axis value. You can determine the indicator based on a given list, looking at the different indicators, which ones would be best for the first equivalence point, which one would be best for the second equivalence point, and then use the Henderson-Hasselbalch equation to determine what are the Ka values of phosphoric acid, that first Ka value and that second Ka value.
In the end, in this experiment, you're performing a number of different titrations, looking at using a titration to solve for an unknown concentration by meticulously adding very precise volumes until the indicator changes color and you have the precise amount where there's a stoichiometric equal amount of titrant and analyte, what's in the flask. You're also going to be doing a titration and preparing a titration curve by measuring the pH after every milliliter of sodium hydroxide is added. From that titration curve, you can obtain a lot of information. The Ka, the acid equilibrium constant, the equivalence points, and use the titration curve to determine what types of indicators could be used to determine where the equivalence points are in future titrations. So these titrations are important throughout a lot of different areas of chemistry where you can use them to solve for unknown concentrations and obtain a lot of the equilibrium information from a titration curve.